Yeah, so it's a real pleasure to introduce Jonathan because Jonathan has been leading this proposal about life in non-aqueous media, and I didn't know anything. And he asked me to participate into that proposal, and it was quite an experience. So Jonathan Lunine is a professor at Cornell University. And he's also the director for the Center of Radiophysics and Astrophysics. Is that
Space
correct?
research.
Space research.
Yep, good.
At Cornell. And he's of course a very well-known. He was IDS. That's how I started to know him. He was IDS interdisciplinary scientist on Cassini, and his research has focused a lot on Titan, but on exoplanets and other planetary bodies, and he's touching at interdisciplinary topics like life on non-aqueous media, which I find just fascinating. So it's really great, and I'm very thankful to Jonathan to lead the effort, and you are really the leader in this workshop. Thank you very much.
So first of all, let me say that Christoph keeps referring to this proposal having to do with non-aqueous life, and it was actually a follow-on to some work that was funded by the Templeton Foundation, of all foundations. And it was to NASA Astrobiology Institute. It actually was not funded, but the science got excellent reviews. And I'm not going to say why it wasn't funded, but just suffice it to say that the referees liked the science. So in our defense, it's a very controversial field. The thing that's not controversial, though, is Titan. Titan actually has large open bodies of liquid that are not liquid water. And the fact that this exists in our solar system is something that we have to confront when we talk about looking for life elsewhere. Do we actually pass Titan by because those surface liquids are not liquid water? Or do we focus on it because Titan is a test case for the possibility that self-organizing chemistry that involves replication and information-carrying molecules and everything we think of that is essential to life actually works in liquid hydrocarbons. If we don't go and check, we'll never know. And some people say, well, let's not bother. What I want to do is to tell you about Titan, the essentials about Titan, in a half an hour. We know enough about Titan now, and it is a complex enough place that you could actually do a course of a quarter or maybe even a semester on Titan and not be stretching things thin in any way. So bear that in mind as I spend 20 minutes telling you about Titan. So this is essentially what we need to know to work this workshop. And how we know it about the clouds, streams, rivers, lakes, and seas of Saturn's moon Titan. So first of all, this is Titan in the optical, and it is covered by many layers of haze that are opaque to the human eye. This makes Titan a very difficult object to study. The essential things you have to remember about it, if you want to think about the possibility of life or self-organizing chemistry in the seas of Titan, are first of all that Titan orbits Saturn. So it's a long way away. It gets about 1.5% at the top of its atmosphere, the sunlight that we get here on the Earth. By the time you get to the bottom, that's cut by a factor of several. So instead of 1,000 watts per meter squared, you're lucky to eke out a watt or a couple of watts per meter squared at the surface. And that means that Titan's really cold. The temperature is 94 Kelvin, but that is actually above the temperature that you would obtain by balancing the incoming sunlight with re-radiation from an atmosphere-free surface. So in other words, Titan has a greenhouse effect, which is a consequence of its dense atmosphere. As a body, it's bigger than the planet Mercury, and it's half rock, half water ice. It's very nearly the largest moon in the solar system. It's lost by about 50 kilometers to Ganymede, which is Jupiter's moon. But there are three moons, Ganymede, Callisto, and Titan, that are just about the same size and the same density, so presumably the same bulk composition. Ganymede and Callisto orbit Jupiter, and Titan orbits Saturn, and we don't understand why there should be this sort of upper limit to the size of these moons. but that's another story. I mentioned the atmosphere. The composition is mostly molecular nitrogen. It's 98%, except down close to the surface, the methane abundance increases. So there it's 95% molecular nitrogen. Methane is almost entirely the remainder. There's molecular hydrogen, which is generated from the chemistry of methane in the upper atmosphere, and there are some other minor constituents in the atmosphere. But because of the temperature and because of the pressure, which I brilliantly didn't put on this slide, so this isn't everything you need to know. You need to know the surface pressure is 1.5 bars at the surface. And by the way, if you use the ideal gas equation of state, which is not too bad for Titan, but it's not great, this corresponds to an air density at the surface about 4 times the air density in this room. So it's a very dense atmosphere and a very extended atmosphere because of Titan's low gravity. And the temperature near the surface is very close to the methane triple point, which is at 90.5 Kelvin. Actually, if you lowered the equatorial temperature or went to the poles in the winter, where you're close to 90.5 Kelvin, the amount of methane in the atmosphere is close to saturation, about 80%. At the equator, it's about 50%, so it's not quite saturated. There are many diverse sources of energy in Titan's atmosphere in spite of the fact that the sunlight is so weak. And I'm going to show pictures of various people who've worked on Titan. This is an eclectic mix. It's not everybody. I'd have to show hundreds of pictures. But Athena Koustenis has done a lot of work with the Infrared Space Observatory and with the mid-infrared device on Cassini and also on Voyager to help us understand the middle atmosphere. And Sarah Hurst, who's a new professor at Johns Hopkins, has done a lot of work on simulating Titan's atmosphere and some of the interesting prebiotic molecules that might actually be made up there. So there are many sources of energy. This is altitude versus temperature in degrees Kelvin. EUV, extreme ultraviolet, gets down to about 700 kilometers altitude. You can see this is a very extended atmosphere. There the temperature is up at around 160 or 170 Kelvin. It rises to the mesopause here, and then it falls through the stratosphere. Sorry, that's the stratopause. It falls then to the tropopause over here at about 50 kilometers and 70 Kelvin, and then it increases as you go to the surface. So you can see this greenhouse effect down here. But again, there's a lot of atmosphere higher up at low density, and it's here where most of the chemistry actually occurs. So EUV, Lyman alpha, lower energy ultraviolet gets down to the tropopause and even a little bit below that. And so there are a variety of places where chemistry driven by sunlight actually occurs. And then add to that the particles, energetic particles from the magnetosphere of Saturn, as well as the solar wind, because Titan spends some of its time in the solar wind and some of its time in the Saturn magnetosphere. And you have a very, very rich chemistry. Now, because of this very, very deep temperature minimum of 70 Kelvin, everything that is made in the atmosphere from methane and nitrogen, and I say everything, condenses out and forms aerosols. And that is, number one, why the atmosphere is opaque, and number two, why we're so interested in Titan, because all of these things that are made fall to the surface and then interact with the geology and the meteorological processes that go on in the lower atmosphere and the surface, and that makes Titan a very interesting place. So if you had to distill the chemistry to its essence, at least what I'm talking about here, it is that methane high in the atmosphere exposed to ultraviolet radiation is broken apart to make radicals. Those will make acetylene. They can also go perhaps directly to make ethane. But Yuk Jung, Mark Allen, and Joe Pinto, whose photo I could not find, wrote a classic paper in the early 80s showing how acetylene could actually accelerate the process of making ethane, which turns out to be the dominant product of photochemistry in Titan's atmosphere. And when these condense out and fall to the surface, ethane is a liquid at 94 Kelvin, acetylene is a solid. And then add into this nitrogen, molecular nitrogen, which also participates in the chemistry, and there's a whole suite of nitriles, amines, and so on that are made. The most abundant nitrogen-bearing product of the chemistry is hydrogen cyanide, which, depending on whose photochemical model you actually choose, could be as abundant in its production as acetylene is. So remember, ethane is the dominant product of the methane chemistry. Acetylene and HCN are abundant, but not quite so much. They are solid at the surface. Ethane is liquid. Now, this process is irreversible because the hydrogen that's liberated in Titan's low gravity escapes to space, and that's actually been seen in Voyager and Cassini ultraviolet images, a hydrogen corona. So the fact that this atmosphere is being lost, the methane is being lost, leads to an interesting conundrum. The observed atmospheric composition is not sustainable over geologic time. All the methane in the atmosphere will be destroyed in something like a few percent of the age of the solar system. So where's the methane being resupplied? Obviously, it would be somewhat surprising if we were looking at Titan at a very special time when we were seeing the last 30 million years of its methane. Plausibly there is a resupply mechanism. And David Stevenson here at Caltech, who was my thesis advisor, and I, and also Yuk-Young, spent quite a bit of time looking at simple models of surface oceans that could resupply methane. It turns out that Titan doesn't have a global surface ocean, but it does have some interesting lakes and seas. And so the resupply may come from the crust or may come from the interior, but not from impacts from comets and so on, at least not in the present day. So this was more or less what I told you, except some of the details about the atmospheric sources of energy really came from Voyager, the Voyager flybys. And they left planetary science with such an interesting set of puzzles that it was very compelling to send the next mission to Saturn, what turned out to be called the Cassini-Huygens mission, equipped with both an entry probe that would land on the surface of Titan and measure various things about the atmosphere, and also to carry with it a radar system, which is here with the communications antenna. This, by the way, is 3 meters across, so this gives you the size of the spacecraft, so that the radar system could penetrate the haze of Titan's atmosphere and actually show us what the surface was like. So these were very large investments in exploring Titan on this Saturn orbiting mission. And Cassini arrived at Saturn in 2004. There are lots of people in the audience who are involved with this mission. Huygens landed successfully in 2005. The orbiter is now in its second extended mission, which will go to 2017, when it will essentially run out of gas and be deliberately immolated in Saturn's atmosphere. This is the Huygens probe. It had 5 instruments. The orbiter has, depending on how you count them, 12 or 13 instruments. This was built by the European Space Agency. The orbiter was built by JPL. So that's all I'm going to say about the mission, but suffice it to say that we would not have a topic to discuss today were it not for the fact that Cassini has been hundreds of % successful. I don't quite know how to express the superlative. It's been remarkable. So I want to start with clouds, rain, and rivers on Titan. This is an image, a montage of images from the Huygens probe. The principal investigator, Martin Tomasco at the University of Arizona, for the camera and spectrometer system. This is a scale bar of 1 kilometer, and what you can see in this image is a heavily dissected terrain, fluvially dissected terrain here, and a heavily fractured terrain filled with some dark material sitting right next to each other. And this area, which it's very tempting to call an ocean, and this is Santa Monica, and there's the airport, but it's not. Okay, it's actually dry. So it's a plain that is littered with various kinds of pebbles, most of which are rounded. They look like they've been pushed around by liquid. And this clearly indicates that liquid has been raining out of the sky and eroding the surface, which presumably, again based on the bulk density of Titan, the surface geology is water ice geology. So this cannot be liquid water, at least not in the present day, and probably never ever. So under the current conditions, it's plausible to say, well, the liquid that's working here is liquid methane. And the Huygens instrumentation was so good, along with Cassini, that we have pretty much I wouldn't quite call it circumstantial. It's close to direct evidence that it really is methane. For one thing, here is the amount of methane, the mole fraction of methane in Titan's atmosphere versus altitude as the Huygens probe descended, as measured by the gas chromatograph mass spectrometer, or the mass spectrometer part of that experiment, led by Hasso Niemann. And you see a couple of things here. First of all, ignore all the different colors. This is a profile of methane, and just let your eye follow it along here. What you see is that at about 7 or 8 kilometers, the methane mixing ratio, which has been increasing in the atmosphere as the probe descends, suddenly becomes a constant and stays a constant at about 5.5% until the surface is reached. So this is a classic profile of a condensable that is forming a cloud. Remember, the temperature is warmest at the surface and it declines with altitude to the tropopause. And so the methane is reaching its cloud-forming saturation level right about here. So there are methane clouds, period. Now, when the probe actually hits the surface, something surprising happened. The inlet for the mass spectrometer is actually on the bottom of the probe and was electrically heated to prevent aerosols from clogging it. And as soon as that probe hit the surface, the methane abundance jumped up by a factor of about 30 or 40% and stayed constant until the probe itself began to cool down and the power failed to the heater. So there's evidently methane in the ground. The surface wasn't liquid. It's more analogous to going out into an arroyo and digging down and finding some moisture in the arroyo. But this is methane, not water. And even more surprisingly, a bunch of other things popped up in the same time period. The landing is shown by the dashed line here. These are abundances from the mass spectrometer. Here's acetylene, cyanogen, carbon dioxide, and ethane. And they all seem, with maybe arguably this one, to have increased in abundance after the probe landed. There's a bit of a delay relative to methane, but that's probably due to the cooling that the evaporating methane from the soil was contributing to this environment immediately around the heated needle. So there are volatiles in this plane, and this is what the plane looks like. And in fact, in analysis of the many images that were taken after landing, done primarily by Eric Karkovska, he was able to find, after some period of time, this little dot that appeared in the lower left-hand corner of the images, corresponding to essentially the edge of the probe. And he interprets that as a methane dewdrop, condensed out from this cloud of methane that's pouring out of the ground. So there's evidently methane on and in the surface of Titan, and it is raining out, we think, and in fact, as I'll show you in a minute, there's direct evidence for that rain out as well. So the other thing one needs to remember about Titan is that it has a very long year, 29.5 years. The seasons are 7 years long. Cassini actually arrived at a time that corresponded to early summer in the southern hemisphere, winter in the northern hemisphere. The formal end of the prime mission was as equinox was approaching, and then there was an equinox mission that spanned northern vernal equinox, so it became spring in the north. And the extended solstice mission is being carried out until essentially the summer solstice in the north, the first day of summer. Now, Titan has a very strong hemispheric asymmetry. There are lakes and seas in the north. There are only 1 or 2 of those in the south. And so it's very important to understand these seasons, but we'll only get half of them from this mission, and that's important to remember. Nonetheless, something very interesting happened as equinox approached. Just past winter solstice in 2004, Titan looked like this in the very red or very short near-infrared, if you will. You see some convective clouds here in the south. It's southern summer. And then at vernal equinox, Titan ended up with this outburst of clouds that was really quite dramatic. This is not the first time those outbursts have been seen. They've been seen from the Earth, and in particular, Emily Schaller, who was a graduate student here at Caltech and worked for me as a Hubble postdoc, led a paper on a cloud outburst that was observed on Titan from the ground, very dramatic one. But in this case, it was possible to get high-resolution images of the surface, at least on a scale of a few kilometers. This is 1,000 kilometers. And what you see in this time sequence from September of 2010 to October and then to January of 2011 is the same region. These arrows are always pointing to the same place on Titan. This region, as the clouds form and pass, gets very, very dark. And then it begins to brighten up again and ends up as, by the time you get to January, about the same as it was in September. Physical media, soils, ground, whatever, turn darker when they are wetted, when liquids are injected into the surface. And so this is very strong evidence that these clouds, in fact, were precipitating and precipitating methane, because that's the only thing they can do based on the Huygens data. So this is a widespread rain system, mesoscale system, having to do maybe with the intertropical convergence zone crossing the equator. And you see a rainstorm and then the aftermath of that. And so this is the process by which the Huygens region is eroded. And indeed, in the radar data from that large antenna you saw on the orbiter, we have images of other fluvial features, but these are very, very broad valleys. This is 100 kilometers. The radar gets 300 meters resolution, and so we cannot see to the level of detail that Huygens did these kinds of small-scale erosional features that we would dearly love to know whether they are ubiquitous across Titan. So to give you a dramatic example of that, here is a radar image of the region around Rome, Italy. This is about 6 kilometers across. There's no scale bar. You see this region is very heavily dissected by water erosion, right? The Tiber River runs down through here. This is the International Airport, Da Vinci. This is 12-meter resolution. Now let me show you what this looks like at Cassini radar resolution of 350 meters. Okay? So you can sort of, if you squint, you can think you see fluvial features, but there's really nothing to see. And you know, this is the best that the radar gets. Sometimes it gets a kilometer, and that looks like that. So we have one area of maybe 20 or 30 square kilometers on Titan where we know there is heavily dissected fluvial erosion due to methane. And we don't know that for anywhere else on the surface. Okay, let me get on to the lakes and seas. The orbiter radar, when it went into the northern hemisphere, imaged these large lakes and seas of Titan. There are hundreds of small lakes, kilometer, sub-kilometer in size. These seas are very large. This one, Ligeia Mare, is the size of Lake Superior. This complex is larger than the Caspian Sea. And this is all on a world that's small. It's the size of Mercury. Now, how do we know that these features are liquid? I've deliberately showed this to you in black and white. The JPL standard is to show the seas as blue and the rest of the area as brown to tell you that the seas really are liquid. But how do we know that? Okay, we actually don't. They're very smooth. They're very dark. When the radar makes images like this, it sends a radio signal not directly down, but at an angle, so any surface that is very smooth will reflect all that radio energy off into space, and it will not be received by the antenna again. So these are certainly smooth features, but you know, maybe they're titanium ice skating rinks for all we know. Well, one of the clues came from the VIMS data, which shows specular reflections off of these features. And Jason Barnes at the University of Idaho has done much of the work on this. This is pretty good evidence that these are very, very smooth and probably liquid features. But the smoking gun for liquids really came from the radar. And it came from the radar in a way that was not expected when the Cassini mission was originally visualized. And that was that with the radar, we can detect not only the reflection from the top of the sea, we can detect it from the sea bottom. So this is work that was actually demonstrated and proof tested by Marco Mastro Giuseppe, who was a graduate student in Rome and now a postdoc research associate at Cornell, and Valerio Poggioli, who is still a grad student in Rome. They use software from Mars radar data to look for the second bounce. As the Cassini spacecraft moves above Titan, if you have a liquid and you have a solid and the liquid's fairly transparent, you'll see, of course, the reflection from the surface, and then at some delayed time later, you'll see a reflection from the bottom, which is attenuated relative to what's on the surface. And that's exactly what he saw. This is not an easy observation to do. There are side lobes in the radar system that can mimic a second bounce, but they have removed all of those. And so here's the sea surface reflection, and here's the reflection from the seabed. And the time difference between the two gives you the depth. So this is the transect across Ligeia Mare, for which they first proof tested this. This is the reflection from the sea surface. This is signal in decibels. The more yellow, the weaker it is. This is the bottom signature. The time difference here can be converted to depth. This is 160 meters. And of course, the bottom signal is attenuated relative to what comes off the surface. Now, if this is methane, if this really is methane, which we think it should be, then there ought to also be ethane present. Because remember that over geologic time, methane in the atmosphere is being converted to ethane, and that ethane is falling to the surface. And in fact, the shape of Titan is such that it should actually be running toward the poles. So we expect that these large bodies of liquid should actually be mixtures of methane and ethane. This is the phase diagram from a thesis by Moran in 1959, temperature versus mole fraction of methane. The freezing points for pure methane and pure ethane are shown here. And then you see that they don't quite form an ideal solution, but they're entirely miscible up here. They do have some solid solutions as you go down to lower temperatures. So we expect methane and ethane, and we expect nitrogen, because the air is 1.5 bars of nitrogen. And nitrogen is soluble in both methane and ethane. It's very soluble in methane, 20%. It's less soluble in pure ethane, 3%. So at JPL, Carl Mitchell and Marty Barmatz actually set up an experiment to measure the absorption of microwave radiation by these constituents. It had never been done before. It's very difficult because these things are fairly transparent. And they were able to make a good match to the Cassini data. What Mastro Giuseppe, what Marco and his colleagues found, was that Ligeia Mare's microwave absorption over that 160 meters one way, 320 meters round trip, corresponds to something that's called a loss tangent, which is a measure of the energy lost. And the value of that is 3 times 10 to the minus 5. Water, ice, and liquid water are 1,000 times more absorbing. So if the lakes were liquid, we would never have seen the signal coming back. Methane is about 3 times 10 to the minus 5. Ethane is about 12 times 10 to the minus 5. So you can take the result, you can take also the solubility of nitrogen and come up with compositions. This is sort of a middle composition, but with the error bars there are more ethane-rich and less ethane-rich numbers on either side. But the main point is these C's are methane and ethane and nitrogen. This is essentially direct evidence. There is no other physical material that has such a low microwave absorption and is stable on Titan's surface. They are methane and ethane. And the amount of material in here, as first pointed out by Ralph Lorenz based on the geology, estimating the depth, and then Alex Hayes based on the bathymetry that Marco did, is hundreds of times more hydrocarbons than the known oil and gas reserves on Earth, but far, far less than what's needed to resupply Titan's atmosphere over geologic time. These C's are the tail wagging the dog. They are not the dog. They're not the main source of methane. The main source of methane lies elsewhere. Now, there are a couple of things about the other constituents I briefly want to talk about. One is volatility. Methane and ethane are the most volatile constituents on Titan's surface, other than nitrogen and hydrogen. This is vapor pressure versus temperature. And then the important solids, acetylene and hydrogen cyanide, are much less volatile than methane and ethane by orders of magnitude. And they themselves have a very extreme difference in volatility. HCN is much less volatile than acetylene is. And so even though they're produced at the same time and they fall out on the surface together, they probably will separate. The poles are colder than the equator. The acetylene over geologic time, these are seasonal and longer term orbital time scales. The acetylene will move to the pole and it'll leave the HCN behind unless the HCN and the acetylene have a chance to react with each other quickly, which they may or may not do. And we'll talk a lot about solubility in the workshop. There are a number of groups that have looked at solubility. James Stevenson, who's a chemical engineering graduate student at Cornell, has done a very detailed molecular dynamics study. Mike Malaska and Rob Hodis have done some experiments. They all seem to agree that acetylene is very soluble in these methane, ethane lakes and seas, but the hydrogen cyanide is really not very soluble at all. The seas do change. This is kind of a remarkable result. Here's a peninsula off of Ligeia Mare in February 2007. Here it is in 2013. This feature appeared. It doesn't appear in VIMS data. This is radar data. This is near-infrared data. But it appears again in 2014 in radar data, and then it disappears. About a 200 square kilometer area. And we don't know what this is, but something is appearing and disappearing in these hydrocarbon seas. It's not a sea monster, but it might be sedimentation or waves or something else. I'm not going to talk about this. I put this in here to as a sort of an advertisement, but I realized when I only had 30 minutes that I just could not talk about this. However, I do think that the right answer, which is one that has been proposed by a number of people, starting with John Lewis 40 years ago. In fact, you can read John Lewis's papers, and it's like the book of John as far as Titan goes. He got so many things right. Just read them. Christophe Sautin, Gabriel Tobey, and others, we've all looked at the effect of clathrate hydrate, methane clathrate hydrate, on the evolution of Titan. It's got a lower thermal conductivity and a higher rigidity than water ice. It probably keeps Titan warm, and it may in fact be the long-term source of methane. There's enough methane in this thin crust to supply 10 billion years of photolysis on Titan. So I'll skip over this. We can talk about all this at lunch. All right, so let me go to the conclusions here. I think the first conclusion is that we should just go to Titan. We know these lakes and seas are there. We know now they're methane and ethane. We know they're subject to various energy sources and geologic processes. What more do you need for a habitable environment? Okay, it's not liquid water. It's liquid methane. But we want to know if self-organizing chemistry can proceed to the threshold of life and beyond in liquids other than liquid water. That would be an astonishing discovery about the real nature of self-organization in the cosmos. And a group of us led by Ellen Stofan proposed such a mission. It just ran afoul of NASA's problems with radioactive power sources and their love of Mars and things like that. But it was a brilliant idea. So my conclusion, the Great Seas are mostly methane, but with an admixture of nitrogen and ethane. Some of the lakes, particularly one in the south, which has been measured in the same way by Marco and company, may have higher concentrations of ethane. The solubility of solids in the seas, which is crucial to understanding the chemistry, varies widely, and this is something that we really need to get a handle on to proceed quantitatively with the kinds of studies we're talking about in this workshop. Remember that nitriles and hydrocarbons have huge variations in their vapor pressures, so they will tend to separate from each other by evaporation condensation processes unless they react first. There is evidence from VIMS data, I didn't talk about this, for some chemistry between acetylene and HCN, because you see cyanoacetylene and possibly acetonitrile on the surface. There are many terrestrial type processes that occur in the seas, but always remember in terms of the chemistry that the temperature is 94 Kelvin. Thank you.